Yes, thank you very much. Let me share my screen, which I hope you can see now. So first of all, thanks a lot, Tomasz, and to the whole team for inviting me here. I was very pleased to be involved with SATEC early on in the first few years. Would be really nice to visit you again once we can travel again and see all the great building of groups and infrastructure that you have done. And I'm also very pleased that actually, despite the pandemic, we recently managed to do some very nice research together, guided by Philip and his PhD student Peter, who was with us for a Erasmus exchange for half a year, and then unfortunately had to leave very quickly once the borders closed, but we got some really nice work done together. So again, congratulations, Peter, for that. And I think Philip might talk about that later in his talk. Yeah, and so when we started our collaboration, I was still mainly at Imperial College, where I at the moment have a reduced position, and I spent the vast amount of my time now at a new institute in Munich that you see here. It's called the Nano Institute Munich. So for those of you that know Munich a little bit, we have the Geschwister Scholl-Platz here. We just had the 100-year anniversary of Sophie Scholl's birth, after which this square here is named. So University Tube Station is here, and there's a big park here called the Englische Garden. Very nice, and we are very fortunate to be close to that park. And we are at the moment surrounded by the veterinary science faculty, which will move out into the north of Munich over the next decade, and a new physics campus will be built. So all of LMU physics, so LMU, I should maybe say, is the University of Munich, will be built up here. And of course, we hope for many more collaborations, Tomasz, with you and your group. Now, so far, most of the work we have done over the last decade or so is in the area of nanophotonics, where we have mainly looked at the response of single nanostructures with light and how we can enhance light-matter interactions at the single particle level. And we've done work mainly in plasmonics, so for surface-enhanced sensing and spectroscopy, for example, then nanoantennas, metallic and dielectric one. Recently, with the arrival of Emiliano Cortes a couple of years ago in my group in London, we have expanded into work on energy conversion and plasmonic chemistry using metallic nanostructures. And we're also doing work on nanophotonic coupling of light via metallic and dielectric nanostructures to 2D materials. So I think many of these topics overlap very nicely with what has been built up at SATEC over the last decade. So yeah, I can only express an invitation to collaborate more on these areas in the future. But what I want to talk today about, also in light of the spirit of this workshop, which is on metasurfaces, is some more applied work, some newer work that we have really only started in the last 24 months, so after my move here to Munich, and that is applications of metasurfaces. Namely, I will talk about some designs that we have done of complex amplitude metasurfaces for holography. Then I will show some work together with the group of Markus Schmidt from the IPHT in Jena, where we print metasurfaces on fiber optics for fiber devices. And then I will finish up with some work that we do in collaboration with a group of Shuang Zhang and at the University of Hong Kong on light harvesting with highly disordered systems. Yeah, so we kind of go to the opposite regime of not having an engineered optical response via order, but via this disorder. What I will not touch upon, but something that excites us also very much, also some work with Markus that we have started recently from Jena, is these kind of cage type structures that you see here, so-called light cages for sensing and spectroscopy. Yeah, so overall, we are moving the group at the moment more into an applied direction. Okay, so let me get started again. These are the three topics, the menu of this morning. We are going to look at holography first, then at meta-optics for optical fiber applications, mainly focusing and trapping, and then some opportunities for disordered metasurfaces in the context of light harvesting. So let's get started with holography. And this is also a collaboration in parts with a group of Patricio Neve from Marseille. Okay, so I don't need to give you an introduction into metasurfaces. Thomas has already mentioned the main opportunity that we have here. I am just putting up one of the seminal papers here by Gaburo and Federico Carpasso, which really nicely showed how you can generalize Snell's law using nanostructuring of the surface. If you just look at this figure here where you see my mouse, right? This is something that every student should know. This is a derivation of Snell's law, which you can do via Huygens surface waves, right? And the idea on how to generalize is that now that we can play with a phase change, that we can introduce now of neighboring points of Huygens surface waves generators, so to speak, by nanostructuring this surface. Yeah, so that can be done in many different ways. One of the most easiest ways is if you put subwavelength resonators, for example, plasmonic rods, onto the surface. Then, as every student should know, as we pass through a resonance of any resonator, actually, right, we get a pi phase shift between the driving force and the amplitude response. So if we now put two of these resonators closely together, we can engineer a 2 pi phase shift, and this way we have complete control over the additional phase shift that we introduce on an impinging plane wave at such an interface. And this way we can generalize Snell's law, and we get basically sub-wavelength control over amplitude and phase manipulation. And this has then led to a whole host of applications. And what I want to focus now on are applications in holography. There's a really nice review article actually in the journal Nanophotonics from also the groups of Zhuang Zhang and Thomas Zentgraf, now already 3 years back. So if anything that I talk about here interests you, go to this article. It gives you a nice overview. Now, if we want to use metasurfaces for holography, the basic idea is that we use the power of the subwavelength unit cell for digitization of a computer-generated hologram, right? And you can do this in multiple ways. So again, I want to just show two seminal papers here. So one relies on the strong scattering response at resonance of plasmonic nanoantennas. So this work here on the left that came out of Cambridge in the year 2014, published in Nano Letters, basically used a subwavelength array of metal rods. Look at my mouse here. So we have basically two like metal rods that in the unit cell that are aligned at 90 degrees angle to each other. And this way you can use one polarization direction to digitize, to encode one digital computer-generated hologram, this one here that you see in the reconstructed image, and you can use the other polarization direction to introduce an other hologram and to encode it. Yeah, and then as you might expect, if you come in at 45-degree angle, you excite both of these resonator modes independently, right? These are orthogonal modes. So we see here a nice superposition of these two holograms. Yeah, so we can use this highly anisotropic scattering response of a nanoantenna to pack information into a metasurface via a digitized computer hologram. So this is, so to speak, the amplitude way. And then you can also do phase encoding, where you use a concept called the geometric phase, which you can manipulate via an array of aligned rods on a surface, and you take into account the additional phase shift that you impart onto a circularly polarized wave as it gets converted from, let's say, left-handed into right-handed circular polarization. This scheme, yeah, called the geometric phase scheme, the first application in holography was from Zhuang Zhang's group in this Nature Communication paper here, has the big advantage that this phase change is basically dispersionless, yeah, so you can work over a broader spectral range. And basically what you can think about is that each of these little rods now act as a point source for the generation of Huygens waves, and then via the interference you can reconstruct your computer-generated hologram. This is a phase-only scheme, yeah? So this is basically good for the reconstruction of a hologram that looks like a diffuse object, yeah, because we lose, of course, all of the amplitude information. So if you look at these nice images here of, I believe these are probably airplanes, yeah, you see you have the image nicely reconstructed via the phase, but you have lost all of the amplitude information intrinsically here. So what I want to focus now on is how can we pack more information density into such a hologram. So we're going to look a little bit at the different ways that you can multiplex, right? Of course, there are many different degrees of freedom, polarization, as I've just introduced in that study from Cambridge with the scattering response and the orthogonal rods. You can think about wavelength, spin angular momentum, amplitude, phase. And what I want to focus about is using the orbital angular momentum degree of freedom. So our goal is to generate a metasurface hologram where we can encode different frames of a movie. And I will show you, actually, we just don't do it with one movie, but we do it with 2 movies. And we encode the different frames into different orbital angular momentum modes and hence get multiplexing out of it. So very briefly, what is an orbital angular momentum mode? It's basically a mode with a helical wavefront. I should say all of this work was conducted by Hao-Ran Ren, who had a Humboldt Fellowship with me and who was actually also from our side the driving force with the collaboration with Tomasz and Philip when Peter was here. Hao-Ran is now back in Australia, where he did his original start into his scientific career and is a research fellow at Macquarie University in Sydney now. So he published a really nice review paper about orbital angular momentum modes. It's just about to come out in a journal in the next couple of weeks, but you can already look at it when you go to the archive here. Yeah, I should also say you will be able to access this talk on my webpage later on, so you can just click on all of these links to get to these papers. So we're basically looking at modes like this. Look at my mouse here in the lower left, modes with a helical wavefront. So the amplitude distribution are these donut beams. Yeah? And metasurfaces have been used over the last 5-6 years or so, both for the generation and for the manipulation of such OAM modes. Yeah? You just see here some cannibalized images from some seminal studies. You have all the proper references to these images when you go to our, to Hao-Ran's, I should say, review paper on this topic. So now we want to use this degree of freedom for metasurface holography. And let me introduce you now, first of all, to a problematic issue there. And the problematic issue is that a conventional hologram does not conserve the OAM degree of freedom, so the OAM topological charge of a helical wavefront. So this was work that was done in collaboration and actually driven by the group of Patrice Genevieve, where Hao-Ran spent a few months before coming to my group. And it shows the first implementation of an OAM preserving, selective, and then also multiplexing hologram, but only for the phase. So what is the issue? So the issue is that if we have a conventional hologram, if you look at the left here, is that during the holographic reconstruction process, so basically think about taking a Fourier transform, right, a spatial Fourier transform of a helical beam, this process is not conserving of the OAM number. So like, what does that mean? Well, if we take an OAM mode and we take the Fourier transform, we can, via some very simple math, convince ourselves that our image, so our pixel, will be a donut mode, if you look at my mouse here, okay? And the problem is now, if we do in a conventional hologram a quasi-continuous sampling of Fourier space, then these donuts of subsequent OAM modes, so with subsequent I mean OAM modes of different order, they will start to overlap. Okay, so these donuts will start to spatially overlap in our image plane, and that will then lead to scrambling of our image. So if we look at this computer-generated example here on the left, we have a conventional hologram here, in the sense that we come in with an OAM beam. We have a continuous sampling in phase space. We take the Fourier transform and we look at the pixel in our reconstructed image, and we see that both the phase and the intensity look just like a scrambled mess. Yeah, and that is due to the fact that our donut modes overlap. So like, what do we need to do? What we need to do is we need to discretize our sampling. So we need to take our image, and we now need to discretize the points in space that we sample this image in. And the sampling constant is now basically defined by the diameter of the donut, in the image plane of the highest orbital angular momentum mode that we will use for the encoding. So if you look at the figure here on the upper left, this shows you the sampling constant versus the OAM mode that we need to use. And you see that the sampling constant starts to linearly increase with the number of the OAM mode. So what we basically need to do is we need to convolute the image that we want to encode. Let's say this rocket here with a Dirac-Comb function, yeah, where the spacing between the different delta functions here is given by our sampling constant. And then we get an OAM conserving hologram, meaning we lose a little bit of spatial resolution of our image, but now we can have a conserving hologram in the sense that if we look at the central part here now, is if we come in with a helical beam front, we take the Fourier transform of it, our pixels will show the nice donut in intensity distribution. Okay, so and then if we then go from that to the next step, we can go from a OAM conserving hologram to an OAM, say, elective hologram. So like what we do here is that we simply add a spiral faceplate of the opposite topological charge of the mode that we want to conserve to it. Yeah. So the idea is then if we build such a hologram and let's say we add a spiral faceplate to the generation of the metasurface distribution here, let's say of topological charge 2, what that then means is that if we come in then with a beam of helical wavefront -2, we are able to conserve that mode, and the readout will now be in a nice Gaussian mode distribution. Yeah, so you see some examples here from simulations. This is for a metasurface where we have added a spiral wave plate of topological charge 2, and you see if we come in with a beam of topological charge -2, we get a nice Gaussian beam point at each of our pixels. Yeah, whereas for the other ones we do not. And then of course what you can then do in the last step, now you can superimpose different OAM preserving holograms of different topological charge, and this way then put into each OAM channel a different piece of information. So for example, A, B, C, D. Yeah? And the idea is then if you then read out with a beam of topological charge 0, so a Gaussian beam, you will get a superposition of all of these. And if you come in with the beam of negative topological charge, you will get these nice letters out. Okay, so let me show you how this got implemented by Hauran in the group of Fabrice in France. So what they used are as scattering elements, small pillars of gallium nitride. Yeah, so this was done via an etching process. And what you see in this plot here, where my mouse is now, is the phase response of such a pillar versus the radius. Yeah, so we kept the height fixed clearly because it's using electron beam lithography, and you see that indeed you can get the whole phase response from 0 to 2 pi via just a modest change in radius. Yeah, and you see some SEM images here. Yeah, and then the actual imaging setup is quite easy. Yeah, it's basically just a 4F setup. So let me quickly walk you through it. So let's first look at an OAM preserving hologram. Again, we take our image from our rocket, we convolute it with the Dirac-Comb function. This way we get our metasurface. And here are now some examples of reconstructed images. So these 4 images which were coded into these 4 different topological charges. Yeah? If we then add the spiral faceplate to it, we get our OAM elective hologram. Yeah, so we take the OAM conserving hologram, we convolute it with a spiral faceplate of the the negative order that we want to read it out with. This way we get the OAM elective hologram, and here in this matrix you now see that the 4 images really only appear right in the diagonal here. Yeah, so we read out here with beam 2, beam 1, beam -1, and beam -2 of topological order. Yeah, and you see the images occur only in the diagonal as you would expect. And then you can use then that in the last step to superimpose for such OAM elective holograms, and then you get like a multiplexing hologram. Yeah, so this is now one plate, so basically one metasurfaces that now has these 4 letters encoded in it that we can now read out with an OAM mode of just the right order A, B, C, D. Okay, so that is all nice, but there are a couple of constraints in here. So here we only use, first of all, the phase, the degree of freedom. So we have a limited amount of multiplexing density, so to speak, and also we get quite significant crosstalk if we only use the phase degree freedom. So you can superimpose actually not much more than 4 of such holograms without getting crosstalk. So what we did then when Haran joined my group, we looked at ways at making holograms for OAM modes that preserve the whole complex amplitude. So not just phase, but also amplitude. Okay, and the trick is there, basically, you need a different fabrication method because in order to access the amplitude, the degree of freedom, we not only want to change the orientation of the rods that we use to digitize our computer-generated hologram, but we also want to change the height. And this additional height degree of freedom allows us then to create a metasurface hologram that is sensitive both to phase and to amplitude. And the fabrication technique that we use that allows us to achieve this is direct laser writing. So we use a nanoscribe dielectric laser writer that got developed and pioneered in the group of Martin Wegener, as I'm sure many of you know. So maybe Martin will show some other nice structures that you can generate with such a facility. So we have used that to great effect over the last year. And what we basically want to do now is we want to generate a metasurface plate where we encode now at 2 different focal length distances 2 different holographic videos. Okay, and the idea is that at one particular distance we can then reconstruct one video, and at another distance we can reconstruct the other video, and we encode the frames of these videos into different OAM modes. So let me first show you a simulation of this. So we have this movie here of this football jongleuring here, where we read out each image with a different OAM mode. Okay, so that will be at distance Z1, and at distance Z2 we will encode an other movie into the different OAM modes. Okay, so we use basically exactly the same recipe as before. So we take for each image frame the image. We ask what is the largest OAM mode that we want to use for the encoding. That sets our sampling constant. Yeah, for our Dirac function that we sample it with, we add a spiral faceplate of OAM phase, and then the only other thing that we do is we actually at the end also convolute it with a Fourier transform lens so that we can do lensless reconstruction. And then we do this for each of the images to generate at the end our complex amplitude metasurface hologram. So now there's only one particular issue, and that's an issue that anybody who is serious about photography will know, and that is the huge dynamic range that a typical image has in image intensity. So this is a constraint basically for the encoding of the amplitude information. And in order to mitigate that, we use what we call an OAM diffuser ray, which basically reduces the contrast of our image. Yeah, so it basically pushes the white point and the black point more towards the center, so that we have not such a large change in intensity and hence scattering amplitude for our hologram. Yeah, but so like then we do this, and we do this for all of the frames of movie 1, for all of the frames of movie 2. Each of them is encoded via different OAM modes, and they are then convoluted with 2 different Fourier transform lenses, so that at one distance away from our metasurface we are able to reconstruct movie 1, and at the other distance we are able to reconstruct movie 2. Yeah, and this way we basically transfer time sequence information into the OAM degree of freedom here. So I said we use rods for that, generated using dielectric laser writing. So the material that we use is simply the resist of the nanoscribe. Okay, so we use the intrinsic birefringence of the polymer rod here now to manipulate the geometric phase via the relative orientation of the rod in plane. Okay, so the geometric phase as we go from LCP, let's say, to RCP, and then we also change the height. Yeah, so we use the intrinsic birefringence for that, and via the height we can change the scattering amplitude. So these 2 contour plots now show height versus length on on both sides, and it shows you the amplitude response, and it shows you the initial phase retardation. And the area that we now choose for our discretization, both in terms of height and length, is indicated by this black bar here. Yeah? So you see via the black bar here, we are covering the whole 2 pi response in phase, and we also go over a significant difference in scattering amplitude. So we now choose 8 different heights, if you look at the lower right, and we choose 8 different orientations. So we have a discretization of our response into 64 levels. So we can this way modulate the complex amplitude in the whole phase space here now. Yeah? So we have the real part on the horizontal axis of the complex amplitude, the imaginary part on the vertical axis, and these stars here basically show you our discretization points. Yeah, so we use that now to discretize our image. This takes quite a long time to write. So here you see now one example of this written via direct laser writing. You see here in green an optical image. So you see we have I think about 2 by 2 square millimeter size here. And if you just look at a frontal view here, so image B, that would be, you nicely see the different orientation of the rods to encode the phase, and you see in image C here in this angled view the different heights of the rods to encode the complex amplitude. And then we can encode 2 movies in there, which I now show you here. Sorry, I need to move the video that I see of myself to the side. So if we look at the upper right here, we have this rotating triangle, yeah, that we have encoded into different OAM modes here. So we use 30 modes here, 30 frames, and we have this rotating spiral. Yeah, these are now real experimental images and encoded into the second focal point. Yeah? And the amount of information that is stored in these images, so basically the length of these images is basically just given by the writing time that we need for our metasurface hologram. Okay, so I hope you found that part interesting. Let me just finish this just to say that now there are of course also other applications of this approach of complex amplitude reconstruction, holography of metasurfaces, right? You could, for example, use it in a context of security and encryption. Yeah, so let's say you have an image that you want to encode securely. So let's say this QR code here, right? You could now use, let's say, a number of image shares, let's say 30 for the sake of the argument, to put the information in. Then you can encode each of these image shares with a different OAM mode. This way you now generate an OAM encrypted multiplexing hologram, and then of course you can only, or your client can only reconstruct that image, that QR code, if the topological charge of these OAM states is known to the client. Yeah, so you can read more about this work. We published it a couple of months ago here in this Nature Nanotechnology paper. Okay, so far, complex amplitude metasurfaces on planar substrates for holography. Let me now show you one application, again driven by Haoran, this time in collaboration with a group of Markus Schmidt in Jena, where we use the same fabrication technique, direct laser writing, but we use it to fabricate such metasurfaces directly on the end facet of an optical fiber, because that is now one of the real strengths of this approach. It's a very versatile approach for nano fabrication, also on more complex geometries, such as this an end facet of a fiber. Let me show you one application here first. I will not go into detail here right now because this is in review at the moment. But what we did here is we took a conventional single mode optical fiber. Then we needed to expand the beam a little bit. So with our nanoscribe, we basically wrote what we call, well, a 3D printed tower structure on it. And then we put a metasurface on it. Again, a complex amplitude metasurface. So just as in holography, we change the direction, the orientation of our elements, and also the height to generate an achromatic meta lens for focusing that works over the whole bandwidth of the telecom range, so over 400 nanometers, which we think is quite an impressive feat. Yeah, and Here you use now the full power of the approach that with the nanoscribe you have access to this extra height degree of freedom, because in the orientation of your rods you can now encode the radial phase profile that you need for focusing, and via local changes in the height of the rods, you can now compensate for the group delay, and this way you can get achromatic focusing. Let me share with you some of the initial results here. So if we look at the upper left here, you see an image. Here an optical image where my mouse is, and below an SEM image of this tower structure, and then there's our metasurface at the end. I will not go too much into like details here, but here in the center part of this slide, you see the focus measured now both in the axial direction, so we have an elongated focus here, and also in the perpendicular direction where we see a nice Gaussian spot there, and you see we basically don't get any broadening over the whole telecommunications range. So from about 1250 nanometers to 1650 nanometers, we have achromatic focusing. And then you can use this, for example, in a context of confocal imaging microscopy in that range with such a fiber. But let me now show you a little bit in more detail some other application. This got published with Marcus just a few weeks ago in the journal Light Science and Applications, and that is to use exactly the same principle, but to make a meta lens on a fiber with a very large numerical aperture. So Marcus in Jena has a large program in optical trapping and biospectroscopy. And what we wanted to see here is, can we use a metasurface to generate a lens with a numerical aperture large enough so that it can trap an object just with one single fiber, so without using any sort of other surface. And yes, it works. So you see here two examples. So we see the structure up here. Again, we have a fiber, we have an expansion section, we have our meta lens on it. Now the assigned for large numerical aperture. Large means larger than 0.8 in water, which is what you need for trapping. And we trap silicon beads and we trap E. coli bacteria. So what you see in the movie on the left here is here where my mouse cursor is, a trapped silica sphere that moves as we move our fiber with our metasurface, and the same here on the right. What you see here is an E. coli bacteria, if you look at my mouse cursor, which we nicely move around via our fiber as well. So just to say, this is quite problematic to achieve from the point of view is that so far, if you have just a single fiber and you put either a ball lens on it or a metasurface or any other focusing device, one was not able to achieve the numerical aperture required without any other tricks. And another trick could be a second fiber or another surface in the distance in order to build an optical trap. So if you go to our paper here, there's a nice survey that we have done where we look at all different ways that you can generate an optical trap on a fiber and the constraints for that. And we overcome this again is because we can use now the height degree of freedom to have an additional tuning knob, so to speak, for our metasurface to generate the numerical aperture reacquired. So just some more details here. So I'm not for fiber, I am not a fiber optics person. So for more details on the theory behind this, please contact Markus Schmidt. But the basic idea is, so we have a single mode fiber. Then again, in order to get an NA high enough, we need to expand our beam, which here we don't do with the tower, but we use fiber splicing technology to basically splice a multimode fiber together with our single mode fiber. This way we are able to extend the beam to a diameter of about 90 microns, which is then enough for the meta lens that we will design in order to get the NA reacquired. Again, needs to be higher than 0.8 in water to trap such a particle. Now, what are the constraints here? Well, the constraints are given on the one hand by the resolution of the fabrication technique. Yeah, so the resolution of our nanoscribe, which is on the order of 300 nanometers axially, and so we need to take the aliasing limit into account, right? This discretization basically sets an upper bound on the achievable phase change that we can get between the pixels. So that's on the one hand, yeah. So from the Nyquist-Shannon theorem, the constraint, and the other constraint is the coherence of the laser source that we will use. Yeah. So if we then look at a plot like you see here on the lower left, which basically shows the focal length versus the lens diameter and the different types of NAs that you can achieve here. Again, you need to be higher than 0.8 in water. The alias limit, both for a 350 nanometer resolution, 330 nanometer resolution are drawn in here, and also the bandwidth limit. Yeah, since you need to have coherent superposition of the Huygens waves that you generate. So we choose these two sweet spots here to now generate two different traps. Okay, and here you see an example of the characterization of the focus of this trap. Yeah, again, axially, we have an elongated focus. In the perpendicular plane, we have a nice Gaussian focus. And then, of course, we can use the full power of that metasurface approach to additionally encode the necessary phase change required into our metasurface to also control spherical aberration, for example. And then the whole thing looks like this. Yeah, so you see again up here an optical image from the side. The more interesting maybe are the SEM images. So you see here the nice cleaved fiber facet of the multimode fiber, and here you see the generated meta lens on it. And again, the meta lens is basically the polymer reassist of the nanoscribe. Yeah, so you see basically here these Fresnel zone plate rings, if you wish, that we have now encoded into our meta surface. Yeah, and on the right here you can see that in the supporting information, in the additional information to this article, you have some close-ups of the pillars actually. Yeah, so we use pillars with 4 different heights to get control over the amplitude response here. And then you see experimental characterization here of the focus, again axially. You see it here on this false color image, and in the plane perpendicular you see the summarized intensity, the integrated intensity profile here in this Gaussian shape. Yeah, and then from that you can determine the numerical aperture, and like indeed it is on the order of 0.9, yeah, which is a record for a single metasurface on a fiber. This takes quite a while to write, yeah, so typical writing time here was 1 hour. Yeah? I should maybe have said early on, so for that hologram that I have showed you, the writing time was almost a day, yeah? So like that also shows you nicely about the stability of this technique. Okay, so I want to get to my third topic, so I'm just gonna increase now the information density, so to speak, by not talking too much about these two slides here, but we then basically used a fiber trapping setup to look at the stability of our trap, the stiffness of our trap. This work was all done in Jena, and suffice it to say we see no appreciable drift over time scales on the order of like a minute. Yeah, so here again, maybe 2 movies here on the left, showing you how we exchange a silica sphere with like another one in that trap. Now the exchange happened, and here on the right you see an E. coli bacteria. This is a sped up movie. This is on a minute time scale here, nicely trapped in our trap. Yeah, and then you can use usual methods such as power spectral density evaluation or mean squares displacement to look at the stiffness of the trap, for example. And as you would expect, due to the elongated focus in the axial direction, our trap is stiffer in the transverse direction than in the longitudinal direction. Okay, so much for metasurfaces. In my last five minutes, I want to switch topics more or less completely, and more or less completely meaning we will now go from an ordered arrangement of nanostructures to a completely disordered arrangement of nanostructures. And I want to show you what we can, some interesting research in the context of light harvesting that we can do with that. This work was conducted by Shangzu Lu in my group. He's a very talented theoretician who has driven this this work, and it was conducted experimentally in collaboration with a group of Xuanzang at the University of Hong Kong. And the basic idea is that we want to generate a material-independent system for broadband yet tunable light harvesting. So from harvesting of sunlight to the surface, which we want to use in a context of enhanced photocatalysis. And the idea here is to use this disorder. Yeah, so some of the students might have heard of black silicon, which is basically highly edged silicon, which looks black. And it looks black because it absorbs light over a large spectral range. And the fact that you can have such broadband light harvesting if you have a very disordered system is actually quite intrinsic. So Shangzu Lu has actually in his PhD work, together with a group of Andrea Frattalotti many years ago, published, I think in 2013, a nice Nature Photonics paper where he gives some very simple arguments why you would expect such a broadband response in a disordered system. And it's actually like quite well known, because whereas in a traditional resonator, you always have a trade-off between energy storage and bandwidth, right? Students just like think about quality factor. If you have an optical system with enhanced disorder, a highly disordered system, one can show that you now have basically many different modes in there. All of these modes divide the total energy available when you excite it from this outside equally between each other. And crucially, you can show that the intrinsic lifetime of all of these modes converges to the same value. And what do I mean by that? What I mean by that is that if you now excite all of these modes optimally from the outside, this is a process known as critical coupling, then you will excite all of them equally strongly. And that gives you then a broadband absorption response. Yeah, so this is something that you can model with a technique called coupled mode theory. And the system that we are looking at now is basically a highly disordered array of colloids. Look at my mouse here in the upper right. Yeah, so for the experiment, these will be silver colloids, but it doesn't really matter. And the idea is that such a highly disordered arrangement now has a multitude of modes. Okay, and we excite all of these modes now from the outside with the same strength, because all of the intrinsic decay constants of all of these modes, so for each mode, you can think corresponds basically to a different color of light harvesting, and we will excite all of them equally strong when we are in the so-called critical coupling condition. Yeah? So the idea is, if we look at these analytical calculations here, we see the inverse of the mode lifetime here. Yeah, the mode lifetimes all have the same value. And what is shown here is the coupling constant to the outside, and we will excite all of this now at optimum coupling constant, and then we get a broadband absorption response. And the first question that we ask now is there a way to modulate this? And there is actually like a nice way to modulate this by now taking this disordered system and putting it on a low-loss cavity. So most simply on a dielectric substrate of a certain thickness, so that you can excite a fibre mode in there. Okay, because what happens then is that for this particular mode now, you increase the lifetime, so you decrease the scattering constant, and now you see, so this arrow will now have a smaller scattering constant. It will move out of this sweet spot of optimum coupling, and hence this mode will be expelled. This mode will be now reflected. You still have a broadband response over the whole spectral range, but for this particular mode. And that's quite interesting, right? Because it's the opposite of what you are used from a fibre cavity. A usual fibre cavity enhances the light storage of the mode that you tune it for, right? Where you have half the wavelength here. Here we have the opposite system. So take your fibre cavity, shake a solution of metal nanoparticles highly disordered on it, and you have now a system where the mode corresponding, where the color corresponding to the fibre mode will not be stored but will be reflected. Yeah, results are published in this Nature Communications paper here. I will, for the sake of time, not go into details, but just look at all these beautiful colors here. This is all the same sample, a highly disordered array of silver particles, just the thickness of the spacer layer underneath is different. So if it's thin, we don't have a fibre mode in the visible, it looks black, just like black silicon. If we start to increase the thickness, you see this shines in these bright colors, yeah? And hence, if you have a wedge, for example, you see, you get all the colors of the rainbow, yeah? So we get it here twice, first order Fabry-Pérot, second order Fabry-Pérot. And this way you can then, for example, encode a nice image into such a substrate where you now just have, in this case, 5 different heights of your dielectric Fabry-Pérot cavity, and you just put a homogeneous disordered distribution of silver particles on it. But what I want to finish with is that the real power of this approach is now is, and this just got accepted, actually came out last week in Advanced Materials, the real power of this approach is now that this light harvesting response only depends on the disorder and not on the material. So if you do the same thing now, but you change the material of your colloid, let's say silver, gold, palladium, and platinum is what we looked at experimentally, the color that you get, the reflected color, does not depend at all on what kind of material you use here, yeah? Which is quite surprising, right? Because of course, all of these 4 materials have very different epsilon, right? They have very different dielectric functions. So if you would just use me theory to look at the scattering and absorption response of a single sphere made out of these 4 materials, they would look completely different. But if we now put them on a substrate, it's only the thickness of this dielectric layer that determines the color and hence the bandwidth of energy harvesting. And that's quite interesting because, of course, the local field enhancement now, which you see here in these simulation, that of course depends now very much on the material that you use, right? Silver is a good plasmonic material. You will have a large field enhancement. Platinum is not a good plasmonic one, but it's, for example, a very good material for photocatalysis. So what you have here now is a way to decouple the light harvesting response from the far field from the material. Okay, you see examples here, experimental ones. That's my last slide. Look at the example of the right side here. So you see here a cross-section image. This is our disordered metal cluster array. And it's this thickness of that dielectric layer where my mouse is now that determines the color. Yeah. So here from Roman 1 to Roman 5, these are 4 different thicknesses. And we do the same experiment now with 4 different materials of our colloids. And you see the color and hence the spectral response of the light harvesting to the surface is exactly the same. So that does not depend on the material. And now what do we want to do with this? Well, now we want to use this in a context of photocatalysis. So we will now look at, in a next step, at colloidal depositions, which will be a superposition, for example, of silver particles and platinum particles. This way you can use the silver to get a high local field enhancement, and you can then use the platinum for enhanced photocatalysis. But the light harvesting itself is only determined by the thickness of this dielectric spacer layer below. Okay, so that was a lot of information, but I just wanted to show you kind of the newest, what we've done here in Munich over the last year with all our fantastic collaborators, of course. So let me just highlight them again. So the early work on the OAM holography, the phase-only one, was done in collaboration with Patrice Genevet, where Haoran went before he came to my group. Then the later part that I showed in conjunction with a group of Yun-Suk Ro, who helped with some of the theory. All of the fiber work was done in collaboration with Markus Schmidt. Everything has been really enabled by Haoran, who is now a Macquarie. And the work at the end on this order was in collaboration, or is in collaboration, with a group of Xuan Zhang. It started when he was just moving from Birmingham to Hong Kong. The cluster deposition to make these disordered clusters was done by Min Han. And with that, I'm at the end. I hope you found this interesting and looking forward to some questions. Thank you very much.
Thank you, Stefan. We now have time for a couple of quick questions, if there are. So please go on.
Okay. So I will take it over. So are there any questions?
I might have one.
Oh.
Stefan, for this nice talk.
Maybe I don't. We have unfortunately just time for one short question. Yeah, but I don't see. Okay, so may I ask you? So concerning that holography, and yeah, What about spectral properties? Is it tuned just to it's monochromatic, or you can tune you also make it more broadband?
You could also you can also make it more broadband. I mean, so the geometric phase response is is pretty independent of the wavelength anyways. The only issue that you will have is that, of course, the birefringence of your polymer will, of course, show a dispersion. So in order to use both the OEM degree of freedom and the wavelength degree of freedom, I think you would need to think harder about the material that you will need to use.
Okay. And maybe I don't see, Ojana, if you see someone who would like to raise question.
Okay, so I will ask Stefan, what is the price tag for this wonderful instrument from Nanoscribe?
It's about, well, you should ask Martin Wegen at the end, maybe via his, I think he still has links to Nanoscribe. Maybe he can give you a great discount on it, but it's on the order of 450,000 euros, basically. Yeah. And it's a very versatile instrument. Of course, you know, you are welcome to collaborate with us. You have your own and beyond. So I also should actually, while I still have the word, apologize that I will kind of go in and out of this workshop throughout because I have to do online teaching here in Munich. So Uriel, I will only be there for the beginning of your talk. Unfortunately, then I have to do my civil servant duties here in Germany and give an online lecture. But nice to see you. Hope you're well.